First off, I'm very honored to be here, and I appreciate the invite. Outstanding presentation so far, and I traveled to quite a few conferences. This is one of the ones. I went to the one in Barcelona that you take something home with you, and you look at your research team and you say, they're doing it right. So ILSI's in my group is really held to a high esteem, and we appreciate the opportunity to speak. So I work with the Iowa State University Polymer and Food Protection Consortium. Some of the data you're going to see today, I would love to tell you it's super exciting, but it's really kind of anticlimactic. So I'm going to jazz it up as best I can. I am required to put IdeoPack up here because let me move forward and I'll explain that. The university requires me to pull anyone up that we got data from to disclose. So some of this data is privately held. Our mission, the Polymer and Food Protection Consortium, is about 4 years old, and our mission is to conduct industry-relevant research and develop solutions, and we focus on design, safety, and functional materials for packaging and industrial applications. I think it's important to note here just quickly, we are privately funded, so very little of my funding comes from FDA, USDA, and SF. We have about 20 companies that fund us, everything from brand owners, very large retailers fund our research. So anytime I go out and ask someone, can I use your data like I am today, I have to get permission. So I actually have to request a data release from every one of my companies. And if just one of them questions it, I cannot release it. So the data you're going to see today is anticlimactic. And I'll tell you why, and that's, you know what, and I'll tell you why it's really good news for us. But I am going to talk about some stuff that's probably a little more exciting. Just to focus on kind of what we do in our research pillars, we look at regulatory compliance and method development. We do a lot of work in PFAS. We just published in PFAS and food and additives and contaminants. It's in proof right now. We do a lot of in-process monitoring. So we work with our companies to develop real-time detection methods, or what I call in-process detection methods. And we have several patents in that area. So Dr. Hartman and the folks before him were speaking, and I think it was Roxy, about the need to do rapid data. We believe in removing the lab and moving it to the line. That's our goal, is to take all the equipment we have in the lab and put it on the line and make it cost effective. We do an excessive amount of work in post-consumer polymer recycling and compatibilization. So our group does a lot of work with chemical companies, modifiers, additives. We've done work in shelf life extension, and just by default, we're doing work in bio-based feedstocks. This is at the request of our retailers. They're asking us to put anything we can that's bio-based in plastic. That's a conversation for a different day, but we do what we're told. I do want to talk about this, and I am going to guess that everyone in this room does not need me to repeat this, but I still think it's very important. I also teach class at Iowa State University. I teach a graduate level class. I work with some of the green initiatives. I work with the folks out in California, Cal Recycle, Californians Against Waste. And this touches me, and it should touch everyone in this room, and I think it constantly needs repeated. Everything we do affects our environment around us, and we all share the same environment. And I tell my students that. And I tell my students when I'm sitting at a green symposium and they're drinking out of their water bottles and their paper plates, and they say green awareness on their shirts, and at the end of that symposium, they throw it on the ground. So we have a lot of work to do with our up-and-coming scientists and students. But there's 8.3 billion tons of plastic waste produced to date. And I can give you references. I don't need to give you references, you know this. Packaging comprises one of the largest market of plastic products. It's got the shortest lifetime. I work with stuff that gets thrown away, the stuff that's on your tables. We've got the Great Pacific Garbage Patch, and then I don't know if you saw, or Garbage Patch, if you saw it yesterday, did you see the dead whale with 55 pounds of plastic? I work in the plastic industry, and those folks fund my research. Large chemical companies fund my research. They want us to find solutions for this, and they are trying to find solutions to this. The problem is the consumers want the problem. They want convenience. So we have a lot of things to work on here. Breakdown of plastics releases harmful materials in the environment. Heavy metals, plastic derivatives, plasticizing agents, bisphenol compounds, and then heavy metals leaching into water sources. So a lot of the folks I work with, and why I say my data today really isn't all that exciting, because the actual migration into the products I look at, or the extractables, really isn't that high, especially with PET. But the retailers I work with, it used to be the focus on the food safety, right? What was going into the water you were drinking or the salad you were putting dressing in. That has shifted. Now we're worried about end of life, what's happening to the product once it hits the landfill and it sits there for a long period of time. So the food safety is important, but the retailers I work with, and they're some of the largest in the country, largest in the world, they are telling me on a regular basis, we just had them in 2 weeks ago for a large meeting at my lab, we are worried about end of life now because our consumers are now worried about what's happening to this material. So food safety is important, but end of life is important. And guess what? It closes the loop to food safety anyway. So it's all the same. So that's some of the work that we do in our lab. We've been doing this for a while, kind of quietly, about 13 years. We've been collecting data. So when I submitted my presentation, I said I'm going to give a presentation about 10 years of RPET data. People might wonder, where did you get 10 years of RPET data? Because we've been working with global suppliers of recycled polyethylene terephthalate for about more than 10 years. And we get data on almost a bi-weekly basis from samples coming from around the globe. So we have a lot of data. We retained all of our samples. So since about 2008, I have samples from around the world from different suppliers, flake, resin, sheet, literally from around the world. I work with brand owners, and when they travel, if they're looking to buy a new resin source or a converter, they will overnight samples to us to qualify them. That's been going on about 13 years, or actually probably greater than 13 years. So we get water bottles, we get shampoo bottles, we get some what we call clean wash flake, we get a lot of solid state resin, we get agricultural plastic, we get mixed stream and marine. I know I have limited time, but I want to tell you folks something else. When we work with our brand owners, we have one very large brand owner that was in our lab recently and said, we get ocean plastic. I'm one of the labs that gets ocean plastic. It's terrible to work with. I mean, I've got a polymer scientist back here telling me, why are we running this stuff? It's so corroded, it's so degraded, it's so bad. To compatibilize it is costly. To build it back up is costly. Well, I'll tell you why we're working with it. Because I have actually 2 large retailers asking me, begging me, can you just put 1%, just 1% somewhere in our supply chain so that we can say we're utilizing ocean plastic. We need to say we're using it, even though I can't find a good home for it. I have emails to back this up. So we're looking for it, and we're trying to do that. But that's the stuff that we deal with every day. So one of the other things we're working on, and then I'll get into the data, I just want to give you some background as to why I'm here and what we're doing. We're developing what we call digital DNA for sustainability. I know there's been a lot of talk about traceability. We believe, given the tools that we have and the analytical tools we have now, we can actually tell plastics packaging can tell a story, and they can tell a very definitive story. So we can look at the influence. What we're doing is basically calling it polymer DNA. So provide digital signatures for data-driven polymeric traceability that closes the loop on sustainability. And we have some publications on this, on how we're doing it using various analytical tools, and we have some patents on this as well. But essentially what we're doing is identifying the influence of post-consumer recycled content on polyolefin and polyester properties, and we're really trying to determine that relationship between polymer properties to predict and monitor PCR content and contamination, either in real time or like we've been developing that database. So we could track it by country. We could track it by supplier. We could track it by resin converter, resin supplier. And then we provide a digital signature of the polymeric material at point of conversion for end-of-life diversion, traceability, and sustainability. So that's how we got to where we are. So we've been collecting heavy metals data since about 2008 on RPET, 2008, 2009. And once a month, we report out to our companies since about 2008, 2009. And we figured something out a while back. We started getting so many samples in from around the globe, our lab couldn't handle it. So I had to contract other labs to do some of our work. And that's okay, everyone does it, and we have to do it because the folks I work with are telling me, hey, I need results back right away. Well, you would think if you send out a method to another lab, or if you ask the lab to run an analysis, that should be very similar, right? Whether it's a digestion, a hot plate, whatever it may be, you should get similar results back. So I want to talk about, we're going to break the session up into 3 studies. And I'm going to go quick, as quick as I can for you, all right? And I typically talk fast. So the first study we found is, remember I said I retained all these samples? We started noticing huge differences between contract labs, our lab, and even other academic labs. PET to digest is not super easy, by the way. And depending on what you're using, whether it's ICP OES, MS, we have some atomic emission going on, there's different ways of doing it. You're going to get very different. We even have XRF. We had labs using XRF and giving us results using XRF. So the first thing we did is we went out and we said, you know what, we need to evaluate the methods for quantification, and we picked one specific, we picked antimony content in polyethylene terephthalate. We used it as our marker because we had a history of what it should be. It was the one that was most developed. So we said we're going to take a look at all the lab practices that are out there, all the methods that are out there, and we're going to determine which one is the best so that when I go to do this huge, we continue to do this, I can tell the labs which method they should be using. Not necessarily because we're an expert, we want agreement between samples. You know, some labs have a way of doing perchloric acid, for example. I don't want to use perchloric. So I'll give you some backgrounds as to why we kind of went down this road. Virgin plastics and post-consumer recycled plastics are polymerized using metal catalysts. I'm sure everybody in here knows this. Issues with antimony consumption. This is another reason we had a large water bottle supplier say they also wanted us to look specifically at antimony. And we did a lot of other metals as well, but specifically antimony for this first study. Quantifying antimony requires digestion from a solid to a liquid state. So we actually have to digest the PET. Previously published methods yielded solutions that had heavy amounts of solid particulate. So this is the issue we ran into. If I go to the peer review, and if I use the methods that are in the peer review that we also talked to folks at FDA about and some other groups that were EPA that were doing some water bottle migration work and extractable work, there was no discussion. And if you look it up, I challenge you, Google Scholar it. If you can't, even on your phone, there's very little discussion on how to handle particulate matter, if any, in the peer review publications. And the method that we were told to use, the Westerhoff method, utilizes, you get quite a bit of particulate matter when you digest it. It's not a complete digestion. So we went out there and we said, okay, we need to understand whether the particulate effects are reliable quantification of antimony levels. And this has all been published as well. So the first step was we looked at polyethylene terephthalates, commonly polymerized utilizing what we call dual catalyst systems. Stage 1, oxides and acetates of magnesium, zinc, calcium, cobalt, magnesium. Stage 2, antimony trioxide. Remember that? Antimony trioxide is the most common second stage catalyst. Insufficient to achieve high molecular weight alone. And then we also realized that there's titanium systems out there are useful, but they cause yellowing and some poor thermal stability. We have seen some new variations on the horizon, so there's some folks out there that may say, hey, we got that figured out. And then we also looked at some materials that were germanium. These are systems produce high quality PET, typically very cost prohibitive. Most of the PET we use is antimony catalyzed. Now, when you look at my data, you're going to see some anomalies in my data. There were some years where there was a push to move away from antimony. So we have some data where the antimony drops out of my historical data. And then it's back on. And this had to do with pricing structures, global pricing structures. It gets kind of unique. But I'll talk about our lab, and then I want to briefly talk about something else. So we get pellets in and we get flake in. There's a method out there for a hot plate digestion. And then there's methods for microwave digestion. Now, and then we have ICP MS and we have ICP OES. We use OES because it's easy, it's quick, and it's kind of the industry workhorse. I call it the Chevrolet of ICPs. And it's reliable. And for the levels we're looking at, it works really well. So we have a newer ICAP. Does everyone on here see that red X over that Anton Par, and I'm just going to use the name because I don't care, that Anton Par microwave digestion system? Do you see that? That company came into my lab and promised me they would give me a complete digestion. We sent samples to them and said, tell me this is a complete digestion. This company did not tell the truth. And I got stuck with it because they said, well, it does do digestion. So anyway, if anyone wants a used Anton Par, I got it sitting in my lab. So secondly, and I please, when you folks are experts, but when I give presentations to new faculty, I tell them, you really need to check your vendors. And some of them are just salespeople. They all are. So just, that's one piece. Secondly, do you see the ultrawave? That one actually works. So, and we'll get into how we looked at different methods. The ultrawave did work. So we looked at 3 methods. We actually looked at many more than 3 methods, but I don't have all day to go into all the methods we looked at. These were the 3 that were most common. These are the 3 that we decided we're going to evaluate. The Westerhoff method is well received. You see it referenced a lot. A lot of publications. I got a lady up here shaking her head, probably knows it well. It's a nitric acid and hydrochloric acids. It's a 250 milligram sample size. It's 180 degrees C for 15 minutes, and it runs about 250 PSI. Everybody see that? So what are we doing right now? We're taking that plastic sample and we're digesting it using these 3 methods, just to get everybody clear. There's also out there called a Takahashi, I hope I'm saying that right, Takahashi method, which is basically a sulfuric and nitric acid, 200 milligram sample size, about 210 degrees C for 20 minutes. And then there's this modified Westerhoff method. This is one that we developed. Nitric and hydrochloric acids, 125 milligram sample, 260 degrees C for 20 minutes, and 1450 PSI. I looked at CEM, I looked at Milestone, I looked at Anton Par, the Milestone, and I get absolutely nothing from Milestone other than a bill for a service contract. It was the only one that we could get to work at these pressures, 1450 PSI. So we stuck with the ultrawave, but here's the issue. Do you see figure 1 and figure 2? We have an incomplete and a complete digestion. The only one that we could get with a complete digestion was the modified Westerhoff method. So that's the method we chose. So let's talk about some of our results. So again, these are just the initial results to determine why we're not getting agreement between labs. And I know there's folks in the room that know this because I've had conversations with them saying, yeah, we get wildly swinging results depending on the operator, depending on the method, depending on the what ICP they're using, how they're using it. So again, we looked at antimony, but we also looked at lead, cadmium, and chromium. And if you look at the bottom there, you'll see an LOD and you'll see an LOQ. The interesting thing about this is we had a big target because if you look at ConAg, the sum is 100 part per million. So we've got a big target. So we looked at modified Westerhoff, we looked at the modified Takahashi, and then we looked at the standard Westerhoff. And we chose the modified Westerhoff. And then the other thing that's kind of interesting is I went back to my research team, and at the time we had a large water bottle supplier working with us, and they said, Keith, we want you to blend it out by percent PCR. So we did. We looked at 20%, 40%, 60%, and 80%. And 100% PCR PET. And we felt pretty good that we had figured out this issue. This is our spike recovery analysis over on the right side. And then we went in, we looked at lead, cadmium, chromium, and you can see some more 4-level blends with virgin and recycled PET. Do you see the variation in these samples? That's common. That's not atypical. That's typical out of almost every lab in the country, by the way. We noticed this. You'll get some pretty serious swings. So anyway, again, using this data from our digestion analysis, we needed to determine which method we're going to use and which method I'm going to require of another lab. So we actually have some other labs we work with. If they don't have an ultrawave, I digest for them and bring it down there. Separations in the antimony values were small. So we selected the differences in lead were much larger. Westerhoff method had the lowest mean concentrations, where the modified Westerhoff had the highest mean concentrations. So for lead, it was different. Significant differences were not observed for cadmium and chromium. So once we selected a method, the method being the modified Westerhoff, we were able to find the greatest repeatability with that method. So what I'm doing right now is setting the framework or the guidelines for how we're going to move into our next study. We needed to select a method that I could get labs that would agree with our results, and we could send them out. So that's what we did. LOQ, near level observed concentrations, not reliable. We found that with the other methods. We would get a lot of variation. We could control that the most with the modified Westerhoff. So I'm going to move on to study 2. So we selected a method. By the way, it's published. You can Google it and find it yourself. The second study is the trends in heavy metal content for recycled polyethylene terephthalate between 2010 and 2018. I actually go back earlier than 2010, but I couldn't get a data release. So I could get from 2010 to 2018. Some of the private companies, specifically one of them is a clean wash flake supplier, I think they're out of business. So I'm unable to find out whether or not. Okay, so anyway, you can see kind of how we collect our samples. We're going to focus today. My team's telling me to move on. That's why I bring them, right? Today, yeah. So do you see in the bottom right corner, do you see that clamshell or that tub? That's a salad tub. So I am fortunate that I have salad tub RPET data going back to 2010. We also have data on water bottles, which I'm not going to present today, and we have data by supplier and by country. So anyway, that is why that's highlighted. So just to back up a bit, about once a week on tubs, and once every 2 weeks. 2 weeks about once every 2 weeks, we get final article or what we call RPET tubs, trace, bowls from all over the country, and in many cases all over the world. So they'll just send them to us. Our lab runs the analysis. And this morning I was sending out a report. So our goal was to quantify the concentrations of heavy metals in recycled polyethylene terephthalate thermoforms between 2010 to May 2018. Chromium, cadmium, lead, and mercury are currently regulated in food contact materials in the U.S. We grouped the samples into 3 quarters within each year of manufacture. So I have all these retained samples going back more than 10 years sitting in a warehouse. We went out and pulled those samples. All rigid. Now, again, we're working with rigid RPET samples were digested using the microwave-assisted digestion we talked about earlier, followed by quantification in a radial inductively coupled optical emission spectrometer, ICP-OES. So this is kind of what we're looking at. Some of the inorganic additives, heat stabilizers, flame-resistant acid scavengers, you can kind of look up there and see them. This is where they are and why they're there. And then we have some additives for polymers, titanium dioxide, zinc, iron, cobalt reinforcement. So we kind of know what we're looking for. So let's get to the not too exciting data. Okay, so if we go back to 2010, and again, these are grouped data points, and this data is pretty fresh. We just got it like a couple weeks ago. We finished doing it. This we're looking at aluminum, and we're looking at cadmium. Cadmium, pretty consistent. And this is data from around the world. These are clean wash flake suppliers from global suppliers. The aluminum data, we have some speculation as to why we start seeing it go down around about, 2015. There seems to be a trend there. We're going to do a lot more data analysis on this. Let's look at iron and titanium. For whatever reason, 2012 through 2016, we start seeing a trend, and it stabilized. And then in the titanium, it was also stabilized right around about 2014 to, right around about, 2 to 3 part per million. Antimony. This data gets weird. I'm here to tell you we've run a lot of plastics through my lab. Antimony typically for us anywhere from on the low end 90 to we've seen it as high as 350 part per million. That's in other products. And these particular clamshell rigid containers, we were running right about where it should be, between 175 to 250 part per million. Then do you see where it drops out? You have no idea how many times I have had to go back through that data because I didn't believe it. Then I figured out after talking to a group of suppliers In the tub world, you know when you go in and you buy the tubs for the salads or the fresh cut, the pre-cuts? There was a time, and we actually went back and found what catalyst they were using, where they switched over to a non-antimony catalyzed PET for a period of time. There are 3 companies that produce it. There was a large plug of it that came through. So actually, the industry, the samples we were getting, it actually dropped out. And there was a large antimony resin supplier that came online that was producing antimony free. I still have their website. And we started seeing a lot of that come through. So that, we think that explains that data. Okay, and then you could kind of see where the data sample was collected, and it normalizes to around 75 to 100. Lead. Really shouldn't see lead at all. We do occasionally see it, but you got to remember, I'm using flake sources. I'm using flake sources from around the world. It's commingled. We try to clean it up, and then we try to re-extrude it. So we do get contamination in there. So let me summarize, then we'll move on to kind of our last study. Antimony and aluminum levels remained mostly constant. It's not that exciting, really. We had some minor trends, but nothing to worry about. We saw typically below 5 parts per million. This one is important, and I highlighted it in red. We have seen this over and over again. Differences were found in feedstocks of RPET between mechanically processed flake and solid state pellets. So there's 2 ways to make resin or to recycle PET. One is to mechanically, what we call clean wash flake. It's a mechanical recycling process. You can also chemically regenerate it, but another really common one is solid stating. I don't have time to get into solid stating, but it's basically a way of building up the IV in the polymer or the intrinsic viscosity, and we consistently see solid state having a higher antimony content than antimony concentration than the clean wash flake. We don't know why for sure yet. We have some ideas, but we're not sure why. And again, the reason we're doing this is the state of California is looking to regulate antimony, and we're trying to provide them with some much needed data to help understand what's out there right now, kind of a survey. And the reality is it hasn't changed much over the years. So then I'm going to finish up quickly, and I know you want me to get moving. So all of this is great. But remember how I talked early on about how the need to move everything from a digestion method to a real-time in-process measurement? We have a lot of companies supporting that initiative right now. So, and this has been published as well. So we looked at assessed the ability of X-ray fluorescence to quantify. We looked at antimony, but then we did other ones as well. We stuck to antimony because we had the most amount of data to compare it to, as a comparison with inductively coupled plasma. Let me explain why this study is important. As we sit here in the room right now, I have companies that have EDXRF systems on their RPET lines that we help design for them that are collecting that data about every 45 seconds. So every 45 seconds, I get a data stream on lead, mercury, cadmium, and chromium coming off of an RPET sheet line. That's an extensive amount of data. And those lines run, the one line's running about 150, 200 feet per minute. We're getting ready to do another install here this spring that'll run about 1,800 feet per minute. That's a lot of data. What we found out was, and I'm not going to get into the background of ICP and X-ray, I'm going to skip that. What we found was this little problem that keeps biting us called infinite thickness. Measured concentration is dependent on sample density and thickness when you use X-ray fluorescence. So if those of you ever watch the YouTube videos, please do go out, Google moms with X-ray guns. It's a real thing. There are people out there that buy X-ray guns from Thermo. The Niton, I think, is a real common one. And they go around to the grocery stores or they'll go at home and they'll post what heavy metal content is in their cookware, is in their plastics, in their packaging. It was so bad at one point we had to help Amazon Whole Foods with a response. So this is a real thing. There are so many problems with that. We're not going to get into that. But what we are going to tell you is, and we looked at this, and we did a lot of work looking at varying the PCR level, or the 10, 20, 40, 60, and 80% PCR. And then we did thickness. We looked at how we could get to that infinite thickness measurement. So penetration depth, or the depth that the primary X-rays travel into the sample. Then we have what we call escape depth that the fluorescence can be detected. And then we have this thing called infinite thickness. For PET, this took us a lot of work to find this, by the way. In our lab, literally working with ANSI to try to develop standards. There are no standards for infinite thickness. Most PET sheets range from about 0.3 to 0.5 millimeters thick. The infinite thickness of PET is about 2.1 centimeters, meaning you're not going to get a good XRF reading unless your sample is thick enough. That's the bottom line. You're going to get all kinds of bogus numbers. When we started doing it with our EDXRF system, we have 2, and they're high end. I called it a random number generator. I said, this makes absolutely no sense. And then we started talking to the manufacturers. They don't manufacture EDXRF systems for this type of research or this type of testing. They're not used for that. So we had to take something that was in industry and try to apply it to a different application. And here you can kind of see the differences in X-ray and antimony content based on exposure time and thickness. This is our really, I'm gonna move fast, all right? This is our really quick experimental design. We took PET samples, 20, 40, 60, 80%. We looked at energy dispersive X-ray fluorescence. We looked at microwave digestion as well, so we split the samples, hit them with an X-ray system, and then brought them down and took them into the microwave-assisted inductively coupled plasma. We collected the data, we did some statistical models, and then we started developing predictive equations so that we could predict what that would be based on the thickness of the material. And it started working really, really well. We made our own samples, so we were doping our own plastic with heavy metals. Antimony standard concentrations range from about 5 to 300 ppm. We scanned them for 2 minutes. XRF is a comparative method. Standards must be used to teach the instrument. So next time you Google something and they're shooting plastic packaging, which they do, you have to teach that instrument, and there's actually an infinite thickness correction factor built into the machine. So you have to tell it. You actually have to tell it and teach it over time what it's looking for. It's a dumb piece of equipment. Detectable and quantifiable limits, detection of smallest concentration that can be measured, and then the quantification, separation of between 2 samples. The LOD for the XRF, 4 part per million, that's not great, but it's good enough for screening. The LOQ, about 14 part per million. So this is our modeling, and then I'll get over to here. We used the 9 unique PET samples. We tested predictability. 34 to 36 were accurately predicted with about a 94% accuracy. This is measured back to an ICP. This means we had to train our system with different RPET samples of different thicknesses to know what we were getting and develop predictive equations. And it worked really, really well. The accepted margin of error is about plus or minus 20%, and we reference the EPA method here. We're using this right now for in-process monitoring. That's where this is happening. And I actually have a website on my phone. The current applications are coal, limestone, and soil, so the XRF guns and machines that you use are not developed for packaging. We modified them for packaging. And let me tell you, that took a lot of work. Relative humidity, distance, time, heat. We had to put vortex coolers on our heads. It's a lot of work. And then I'm not going to get into the issues with the Koenig TPH, but these are our detection limits. And our next step is, of course, to develop a protocol to evaluate the 4 Koenig for regulated heavy metals. We're already doing that. It's already in process. And I know you want me to wrap up here. So I'm just going to acknowledge some folks that helped us with this and take questions.
Thank you very much.